All right, so it is 3:30. We can go ahead and get started. Yeah, how's everybody doing today? Hopefully everyone's staying warm and not slipping and falling on the ice. Yeah, hopefully the weather will turn around eventually, although I do know this is pretty standard Illinois weather. Again, please don't look at the bottom right-hand side of my screen. It's I do apologize for that. But yeah, so let's see here. I'm just trying to code switch for my 207 class, which I literally just left 1 minute ago. Yeah, so a couple of housekeeping elements before we get started. So I did send out an email on Friday indicating that I had posted our first homework assignment on Canvas. So that first homework assignment will be due this Friday. And basically you can expect another homework assignment hosted this, essentially this Friday night. And so basically that will be the general structure of the class. We'll have a new homework assignment due every Friday night. I tend to like to get my grading turned around within a week. So roughly about next Friday, you should be able to receive your grades as well as comments and solutions for that given homework assignment. And again, if you have any questions about a particular grade that you got on that homework assignment, if you wanted to basically do a regrade request, do go to Jordan with those questions. And basically you do have a week to make that regrade request after basically after you received the grade on that particular assignment. Yeah, and so basically what we're going to do today is finish up with a few remaining on Unit 1, which again is basically walking us through an example of us going through the full data science pipeline, particularly performing a cluster analysis on a given data set, which is comprised 10 average ratings that a 980 vacationers gave to 10 different types of trips on TripAdvisor. And then next, what we're going to move on to is Unit 2. So you should be able to see those notes on the course schedule. And then basically Unit 2 is going to talk again about cluster analysis, but the point of Unit 2 is in essence to give us a roadmap of all of the variety of different clustering algorithms that exist in the literature. Or in other words, an organizing schema, which can help us not just learn about existing clustering algorithms that exist, but also perhaps give us insights as to how we might go about designing our own clustering algorithms, if that's what we want to do, if we find that there's a particular data set that is not well suited for the existing clustering algorithms that exist out there. So that's basically what we have coming up. So any questions before we get started? Okay, so hopefully you had a chance to notice that I did post a quick warm-up poll here, essentially asking how we go about interpreting what we called a k-means elbow plot, which we discussed on Thursday. And again, what this k-means elbow plot represents is the average inertia of a series of clusterings of a given data set clustered into one cluster, the average inertia of a series of k-means clusterings created for a given data set in which we were clustering it into two clusters, so on and so forth. So the question here is, what interpretation do we make if we see this elbow plot, which really does not have a strong elbow, something like this? So let's see what we said here. Okay, so 47% said true. The only interpretation that we can make based on what we see here is that the data set is in fact not clusterable at all, and that cluster analysis should not be used. So actually, the answer to this question here is actually false. So this could be one potential interpretation that might in fact be the case if we saw a k-means elbow plot that looked like this. But there's actually two potential things that could be going on. if in fact we do not see a k-means elbow, or excuse me, a strong elbow. So there's actually two things that could be the case. So it could be the case that the data set is simply just not clusterable at all. So it's basically just a blob with no meaningful separations at all. On the other hand, it could actually be the case that that there is a clustering structure in the data set. So maybe something like this, but it happens to be a clustering structure that k-means is not effective at identifying. So you want to remember, k-means is more or less effective at identifying a given clustering structure, provided it meets the following ideal specifications. So generally speaking, if your data set, satisfies these ideal specifications, k-means, generally speaking, will be able to identify these, the inherent number of clusters that exist in the data set. On the other hand, it is possible that even if a given data set does not meet all of these specifications, it is still technically possible for k-means to still identify the inherent clusters that exist in the data set. So for instance, what we're going to explore in Unit 2 is that even though a data set such as this does not meet all of the ideal k-means clustering specifications, it is actually going to be the case that k-means will still be able to identify these two clusters, even though they are not spherical. Okay, so one of the reasons why we'll see is because these two clusters are so well separated, k-means will actually still be able to effectively identify them. But that's something that we'll explore in Unit 2. But the bullet point is, again, when you see a k-means elbow plot with no strong elbow, either it means that the data set is not clusterable, or it is clusterable, but k-means will not, or is not designed to be able to effectively identify this clustering structure. Okay. All right. Any questions on that? All right, cool. So just wanted to wrap up with a few additional things that I wanted to talk about when it comes to not just the k-means clustering algorithm, but also how we might go about integrating any given clustering algorithm into the full data science pipeline. So, like we discussed, clustering, so the task of clustering in general, is a unsupervised learning analysis. So in other words, we are not given an answer key. So we're not given a response variable within the data set that we have in our hands to predict, to essentially design a model that will predict that response variable. So what that means is that the task of knowing if our clustering algorithm did well or not so well is a much more complicated ask. So given that we don't have an answer key of the response variable, we need to be more sophisticated. It's a little bit less clear as to how well our clustering algorithm actually did. So we need to be thinking about sophisticated ways, or I'll say insightful ways, for evaluating how well our given clustering might have done. So one such ways that we might go about evaluating a k-means clustering, for instance, is by simply just looking at the objective function value that we're in essence trying to minimize with the optimization problem or the algorithm. So for instance, we might simply just compare the inertia of two k-means clusterings. And in theory, we might say, well, the clustering with a smaller inertia, i.e. the smaller value that we're essentially trying to minimize, might be the better clustering. But what we're going to see is that simply just using inertia and inertia alone is not necessarily going to give us the most insightful clustering overall. And another thing that we want to think about is that if we are going to use the inertia to compare the, let's just say, quality of two clusterings, we want to make sure that we're just comparing the inertia of clusterings performed on the same data set. And so why do you think that might be? So why is it not a good idea to compare the inertia of two clusterings created for two different data sets? Any ideas? All right, so let's take a look at, yeah, exactly. It has something to do with sparsity. Yeah, so for instance, let's just say we have this data set here and our inertia for this clustering of this data set would simply just be the sum of the squared Euclidean distances of each of these observations to their respective cluster centroid. But let's just say we created, we had this other data set which looked very similar, except maybe the scale of the data set was shrunk to a degree. So maybe let's just say we just simply just took the x-axis value and the y-axis value of this plot, and we simply just like divided by 2. And let's just say we created the following two respective clusterings here and here as well. So these are our new data points. These are our new centroids. And so this was data set 1, and this was data set 2. So which one of these data sets would we, or excuse me, which one of these data sets and their respective clusterings would we assume to have a smaller inertia? So data set 1 or data set 2? Yeah, exactly. So we would assume that data set 2 and the clustering that we just created is going to have a smaller inertia, simply just because the sum of the squared distances of each of their points, or each of the points in data set 2, is going to be a lot smaller than the sum squared distance of the points in data set 2. But simply just by looking at these two data sets and these two clusterings, I don't really see any strong indication that clustering 1 is any better than clustering 2. So therefore, in order to use inertia to get a more comparative performance, if you will, it's only a good idea to compare the inertias of two clusterings that were performed on the same data set. And what you might say is, if you're comparing two inertias of two clusterings of the same data set, you might say that the clustering with the smaller inertia is better. But big caveat here. So there's an exercise on the course website. We're kind of running a little bit low on time, so I don't necessarily want to go through this whole exercise. But let's just say, for instance, we decided to cluster this data set here into two clusterings. Now, technically, if we had created a k-means elbow plot for this data set, what we would have ended up seeing most likely is the strongest elbow showing up here at k equals 20. We would have seen that in all likelihood, this particular data set has about 20 inherent clusters that exist in the data set. Now, let's just say, for instance, we decided to not cluster the data set into 20. So maybe we didn't know about the k-means elbow plot. And so let's just say we decided to just cluster this data set into 4 clusters. So let's just say we ran k-means twice, okay? Now, what we're going to end up seeing is basically in Python, if you run k-means without fixing a random state, then it's entirely possible that each time you run that function or each time you run that algorithm, you could, in essence, end up getting a different clustering result. So for instance, if we ran the k-means clustering once, looking for 4 clusters, then we might have gotten this result. And for instance, we might have gotten a different result if we had run it at the same time. Now, the thing here is one of these clusterings has an inertia, I think something around 12,400, something like this. So let's just say this clustering had this inertia. And then technically, this clustering, I believe, had an inertia of something like this. So in theory, these are two separate clusterings of the same data set. And so in theory, we might say, well, okay, this clustering is the better one. But given what we're seeing here, that's not necessarily the right approach. Who's to say that this is actually a better clustering than this clustering? Now, technically, I think the best clustering would be the one in which we, cluster the data set into 20 clusters. But basically what we're seeing here is if we chose to cluster this data set into just 4 clusters, we're actually getting a different clustering that perhaps might just represent a different facet of the data set itself. So what I want to summarize here is that first, again, k-means may return different clustering results each time you run the algorithm. And the reason why is because we randomly initialize the centroids in the first step of k-means. Okay. And it is possible that some results may be better than others. But on the other hand, as we're seeing here in this example, some results may represent simply just a different facet or aspect of how the data could be grouped and may not necessarily be worse than other clusterings with a lower inertia. Okay, and the reason why that we might, again, end up getting different results is, again, you want to remember that the k-means clustering algorithm never actually, or is not guaranteed to end at the absolute global minimum of the inertia function. It's only guaranteed to converge to a given local minimum. So based on where your initial centroids are, you may actually end up arriving at 2 different local minimums, essentially. Okay, so because of that, Lloyd's algorithm, or more colloquially, the k-means clustering algorithm, is what we call a non-deterministic algorithm. Okay, and again, what this means is because a non-deterministic algorithm is one in which even with the same input and the same parameters, you can get different results based on different runs of the algorithm. Okay. All right, questions on that? Okay, so that's something that you would want to keep in mind. And so now, given that you might know that a particular algorithm that you're using is non-deterministic, what are some potential ideas for how you would go about handling the non-deterministic nature of a clustering algorithm? Run it with different inputs. Yeah. So I would say, yeah, repeating so rerunning the algorithm multiple times might be a good idea. Another idea would be to fix a random state in the k-means function for reproducibility. And if you decide to rerun the algorithm multiple times and you do, in effect, get different results, then you would want to think about, well, how do you, what do you do with all those different results? Do you try to pick the best one? Do you perhaps try to combine those slightly different clustering results into one? So these are all questions that you would want to think about. Do you choose the best clustering? And then, if you're indicating that one clustering is better than the other, you want to think about how do we define the best clustering. And if you choose to not, just select the best clustering, you might think about how might we combine multiple different clustering results? Okay. All right. So before we move on from talking about k-means, I wanted to talk about some general benefits and drawbacks of k-means. And so there's a reason why, k-means is introduced in, kind of basic data science classes. So one of the main benefits of k-means is that it generally tends to be one of the fastest clustering algorithms that exists out there. Now, unfortunately, it does start to break down when it comes to big data clustering. So for instance, trying to cluster a data set with like hundreds of millions of rows or hundreds of millions of columns. But generally speaking, if you're not dealing with big data, k-means clustering does tend to scale well, particularly as the number of observations grows or the number of attributes grows. And there's another reason why it's often introduced, especially at like the stat 100 level. So we talk about it in stat 107. It does tend to be one of the easiest clustering algorithms to understand. So that is a nice benefit, not just for, not just if you're a student trying to learn how an algorithm works, but also if you are a data scientist and you're trying to explain how an algorithm works to, let's just say, your boss or your client. So the more explainable an algorithm is, the more trust you essentially develop with that boss or with that client, which can be, has a whole sort of slew of beneficial, aspects as well. But it does have some drawbacks as well. So we've seen some of those already. So one issue is that it only tends to work well, or it's only designed to work well with certain types of data. So we saw these 7 ideal properties for identifying clusters with the k-means clustering algorithm. In addition, you also need to pre-specify the number of clusters that you're looking for in k-means. So, if you don't have a clear sense as to the right number of clusters to ask for, this, at the very least, requires an additional set of analyses to determine, what is that right or inherent number of clusters to ask for. So one potential solution that we introduce for determining the right number of clusters is to look at the k-means clustering, I'll just say the k-means elbow plot method. But what was a downside that we identified when it came to using the k-means elbow plot method for determining the inherent number of clusters that exist in a data set? So if we're trying to determine how many inherent clusters exist in a data set, will the k-means elbow plot be able to identify that ideal number every time? Exactly. So someone's saying we may not be able to identify it if there's no elbow. Right. So basically, if your data set is not the ideal type of data set that k-means is designed for, then the k-means elbow plot may not, or may similarly not be able to identify the number of clusters that exist in the data set. In other words, the k-means elbow plot is only designed to detect the clusters that k-means itself is able to detect. Okay. And also, yeah, the elbow plot can be subjective. So sometimes it's difficult to see like what is the elbow. But generally speaking, the elbow tends to be the point in the plot where the difference of the slopes is the most dramatic or the most different from each other. And then one other drawback that we just discussed is that it's a non-deterministic algorithm. So you'd want to think about, how do you deal with the inherent random nature of your k-means clustering results? Maybe you'll run it multiple times. Maybe you'll fix a random state. So these are all decisions that may impact the type of, long-term results that you end up, essentially wanting to get with the algorithm. Okay. All right. Questions on that? Okay. All right, so I added on some additional video content after Thursday's lecture, essentially talking about how to go about using the scikit-learn k-means function to actually, go about clustering this given data set that we have in our hands. So yeah, so let's just say we've clustered the data set already. So basically that, again, cluster analysis is a more sophisticated type of descriptive analytics technique. And so let's think about how our descriptive analytics results may actually feed into other parts of the data science pipeline. So for instance, maybe we want to use our clustering results, for instance, to make predictions. So this is a valid question that we would want to think about as data scientists when it comes to running an algorithm, and perhaps what we might want to do if we were to get new observations that were not actually run in the first iteration of the k-means clustering algorithm. So for instance, let's just say you have this data set in your hands, you ran k-means on that data set, and you found the following clustering here. Now let's just say you had a batch of new observations that you wanted to furthermore cluster. You wanted to cluster that observation with one of the existing perhaps clusters that you have here. So the question is, from a time perspective, so let's just say this is a really big data set, we'd want to think about, well, do we actually need to rerun the entire algorithm again to cluster just this new point? And if not, what are some potential workarounds that we could try? So that's one question I want you to think about. I'm going to open up some breakout rooms in just a second. So I want you guys to discuss your answers to that question. But then there's another question that I added here as well. So let's just say you are able to come up with a way to cluster a few new observations, let's just say, into the existing clustering without rerunning the whole algorithm. So can we think of any instances in which we may not want to do that? Or in other words, in which we may actually want to rerun the whole clustering algorithm again on the full data set. Okay, so I want you to think about that and discuss it in your breakout rooms for maybe just a few minutes here. How many people? Okay, so I'm going to open up, let's say 15 breakout rooms. Okay. All right. So I just opened up a series of breakout rooms. So I'll let you guys choose the rooms that you would like. Try to go into rooms of about 3 to 4 people. In the interest of time, I'm just going to start randomly assigning people to the rooms. If you'd like to change, that's totally fine. Yeah, and so basically discuss your answers to these 2 questions here. And then in a few minutes, we'll meet back and discuss. And again, another benefit of going into these breakout rooms is you can get to know some of your classmates, kind of suss them out to see if they want to work together in a group project in the end. Okay, so everybody should have been assigned to a breakout room. So we can go there now. We'll meet back and discuss. All right, so I just closed the rooms. So yeah, interested to see what people think. So we had already clustered a given data set already, and we added a new point to this data set or a new set of observations so that this data set. Do we necessarily need to rerun the k-means clustering algorithm again? And if not, what can we do instead? So what did we say? Um, so we can manually assign an observation to one of the existing clusters. And then how might we go about doing that? Yeah, exactly. So one way that we could go about doing that is simply just to assign that point to the closest existing centroid from the last clustering that we created. Yeah. So we don't have to rerun the algorithm. We can simply just assign each new point to the closest existing centroid found when we clustered the original data set. Now the question is, do we need to calculate a new centroid for the existing cluster? So you could do that if you wanted to. So first you could, assign each of the new observations to their closest existing centroid. So for instance, you could do the cluster assignment step all at once for those new observations. And then furthermore, if you wanted to have a more accurate centroid that better reflected the existing clusters that you now have with the full data set, you could recalculate each of those centroids again, if that's what you wanted to do. Yep. Now, the second question is, can you think of any instances in which you might actually want to rerun the whole clustering algorithm again? Yeah, so somebody said if it's more than just a few new observations, well, I think it depends on the nature of those new observations. So let's just say, I found there's a lot of new observations, and maybe one of them was here, maybe one was here, maybe one was here, 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 something like that. Would it be that big of a deal if we simply just assigned these particular points to their closest centroid? Yeah. Yeah, so it might be not that big of a deal if we were noticing that our new data points tended to be relatively close to maybe existing observations in the original data set, or maybe the current centroids that we had. But let's just say, for instance, what if we saw like a new batch of observations started to display this completely new pattern? So something like this, where they were all relatively far away from the existing clusters and centroids that we had identified. What this might make us suspicious of is that perhaps the original data set that we had was actually not fully representative of a much larger data set that we might actually want to cluster. So for instance, the new data may in fact be more representative of this much larger population. And in essence, it's possible that new inherent clusters from the full data set, the larger population, might actually start to manifest. So if we had, new observations that were representing this, this potentially distinct cluster that we hadn't identified, then unfortunately, by not rerunning the whole algorithm again, each of these observations are going to be split into the existing centroids and clusters that we had already identified. But on the other hand, if we had rerun the entire algorithm again, if we had rerun the k-means elbow plot, we would have identified it's like, we're actually seeing 4 clusters that now exist in this new data set. So maybe we should cluster the data set into 4 clusters. So we want to be careful about considering whether your new observations and original data sets think about, whether your original data set was representative of the the full data set with new observations. If not, it's possible that your new observations may belong to a new inherent cluster that your original algorithm did not detect. Okay. All right, something to think about. Any questions on that? Okay, that's how you might think about incorporating new observations. Now let's also think about, a data cleaning decision, or perhaps, like a data cleaning decision. So let's just say, for instance, most of our observations in a given data set had a complete set of values. So we had the x-axis value, we had the y-axis value. But let's just say, for instance, there were a couple observations in which they had a missing value on, one of the attributes. So for instance, this observation, we know the x-axis value, but the y-axis value is missing. So what are some ways that we could attempt to cluster these observations with missing values? Yeah, so we could simply just cluster by the x value. Now, the thing here is, would we be able to, given the way that k-means works, or the way that we introduced it to you guys, would we be able to use this point in the algorithm itself, or would we have to introduce it in the end after we'd already clustered the data? Yeah, so there's actually a couple of things that you could have done. So one thing you could have done first, right, is you could have maybe taken your data with missing values, and you could have, rather than dropping them, you could have imputed those missing values. But we want to be careful about, especially for cluster analysis, how we go about imputing those missing values. So let's just say, for instance, we decided to impute our missing values with, one of the standard approaches. Like, let's just say it was, we imputed all of our missing values with a 0. And let's just say there was a lot of observations with missing values. So we had, x-axis values, which we knew, but the, y values were missing. So we had a series of observations that we imputed to be here, a series of observations that we imputed to be here, so on and so forth. So what might this do, this particular data imputation technique, what might this do to our cluster analysis if we approached missing values in this particular way? So for instance, if I were to take this data set that I had cleaned in this particular way, where do we think that we might see the elbow? Yeah, it might increase the cluster. So it's possible that even though technically this data probably only has 3 inherent clusters, by creating a k-means elbow plot with data imputed with 0, in this particular scenario, it's possible that we may end up seeing these additional, clusters forming that actually aren't all that meaningful. It's entirely possible that these observations probably belong to this cluster. These observations probably belong to this cluster. But because of this particular imputation method that we use, we actually ended up creating these 3 additional meaningless clusters. So you want to think about, your data imputation techniques, what you end up doing with your missing values. Now, one other thing that you could have done, for instance, is you could have simply just, temporarily dropped all rows with missing values and simply just clustered the data in which you had complete information. Now, if you wanted to, you could have taken these observations with missing values and then, for instance, do like we did in the previous part of this lecture notes, in which we just cluster the observations in at the end. So for instance, I could see that at the very least, the centroid, or the closest x-axis value of my centroid, is this centroid here. So basically the x-axis value of this observation is closest to the x-axis value of this centroid. So for instance, I could end up, in an ad hoc fashion, assigning this, missing value observation to, this particular cluster here, based on the values that I actually do happen to know. Okay, but then unfortunately, we do end up, leaving out this potentially, useful information. So in essence, like we were not actually allowing for this value in the observation to contribute to the overall clustering structure. So that is a downside as well. Okay. All right, questions on that? Okay, so again, when you're going through your final projects in the end, you do want to be very careful about every step of the data science pipeline, really thinking carefully about how each of your, for instance, pre-processing steps may in fact impact your overall cluster analysis. Okay, so the final step here is, again, there was a purpose to, why we were clustering this data set in the first place. So again, one kind of cheesy example here is my friend who wanted to open up a yoga studio. She wanted to find a cheap set or subset of people that she could, advertise her yoga studio to, and in all likelihood, or have a much higher chance of having these people actually want to, attend her yoga studio. So maybe this is a little bit more of an American-centric, I guess you could say, qualitative analysis that you might conduct at the end. But for instance, after you've identified the clusters that exist in a given data set, you want to explore, what attributes actually characterize each of these clusters that you found. So for instance, I can see from my side-by-side box plot visualizations here, you can learn a little bit more about what the people in cluster 2 actually like. So for instance, it looks like the people in cluster 2 have a much higher preference for, establishments such as juice bars, lower preferences, or let's just say religious institutions. And then they have higher preferences for museums, as well as resorts. So what this might be indicating, about the type of people that are clustered into this cluster 2 is, perhaps this is some indication of, secular, health-conscious interests, let's just say. So it's possible, you might take this analysis to an actual, advertiser, someone who's more of a subject matter expert about, what types of activities really interest people. And they might say, okay, I can see that, secular health conscious people are, more likely to also be into a yoga studio. So that, that expert, that subject matter expert might say, that these people might also be interested in new yoga studios in the area as well. Okay, so this is an example about how you might actually take your unsupervised learning analysis, your descriptive analytics, and use it for prescriptive analytics purposes. Or in other words, how do you use your insights to come up with the best prescription or the best decision for, let's just say, your business. Okay. All right, so that basically concludes Unit 1, just basically going through the full data science pipeline, particularly when we are conducting a cluster analysis. And we talked about how to use k-means clustering as one such type of cluster analysis. Okay. All right, so any questions before we move on to Unit 2? Okay, cool. All right, so Unit 2, again, like I mentioned, is going to provide us with a roadmap of basically all of the different types of clustering algorithms that exist in the literature. So a second here. So what we want to remember is the k-means clustering algorithm only works, or is only designed to work well, for certain types of data sets. So for instance, there are types of data sets in which, they're all numerical, the data set doesn't have a lot of noise and outliers. You know the right number of clusters to ask for. But then in particular, it's not just making claims about the type of data that you're dealing with, but then also the type of cluster that you're dealing with as well. So in this particular case, the way that we're defining a cluster, particularly a type of cluster that k-means can identify, is, essentially we're assuming that a cluster is spherical, that clusters all have the same sparsity, they all have the same number of objects, and they're well separated from each other. But we've seen other examples of how we may also choose to define a cluster that does not necessarily meet all of those specifications. So we want to think about how might we define a cluster such that a clustering algorithm is in fact able to identify these different cluster types that we can kind of see with our eyes. So the purpose of this unit here, essentially what we're going to do is we're going to go through a series of two-dimensional data sets, all of which do not meet all of the ideal specifications for k-means clustering. And we're going to explore what k-means actually does to learn a little bit more about why k-means is specifically designed to work well for certain data sets as opposed to others. And in so doing, by examining these unideal data sets, it's going to allow for us to develop an intuition as to how we might develop a clustering algorithm ourselves that doesn't necessarily meet all of these ideal specifications. And then in particular, also give us a language or a different set of different definitions for how we might go about, defining a particular cluster. And so basically all of these different definitions of clusters that we're going to, come up with essentially dictate or help us organize all of the many different clustering algorithms that exist in the literature. Okay. So let's start with one of the most common cluster definition types. So we start with, one of the most common cluster or types of cluster, or ways that we might define a cluster is what we call well-separated clusters. So this is a pretty basic definition. We simply just say that a well-separated cluster defines a cluster only when the data contains natural clusters that are far apart from each other. Okay. Now, as we're going through each of these different cluster definitions, again, like we're seeing with a lot of our initial definitions, the definitions that I'm giving you here are going to be very vague. So what is vague about this definition here? Yeah, so what does it mean for two clusters to be far apart? So we might ask that. Or I might also ask, how far apart do two sets of observations need to be in order to be considered two clusters? Okay. Now, again, we're giving you all of these vaguely stated definitions because, there's actually a wide variety of ways in which you might go about answering these questions. And the variety of different ways that you might go about answering these questions also dictates or defines the myriad of different clustering algorithms that exist in the literature. Or in other words, the different well-separated cluster-based algorithms that exist in the literature. So let's take a look at an example of a well-separated or two clusters that fit this well-separated definition of a cluster. So this cluster here and this cluster here. So we're going to cluster these two, or we're going to cluster this data set with k-means, but we're going to think about first how k-means might actually perform if we were to try to identify these two clusters. So first, let's think about this. So does this data set meet all of the ideal properties for the k-means clustering algorithm? And if not, which properties are not met? Should I do a poll? Yeah. So yeah, the answer to the first question is no. It does not meet all the ideal properties. And there's actually two properties. Oh, sorry, excuse me, one property that is not ideally met. And so that is the two clusters, the two inherent clusters that exist in the data set are not spherical. Okay. We want to think about, would k-means actually still be able to identify these two clusters nonetheless? So to think about or to determine how k-means might perform, it's fruitful to think about where roughly would be the two centroids of the two clusters that we've identified here. So again, the centroid is simply just the average of the, all the x-axis values and all the y-axis values of a given cluster. So I would say the average of all the points in this cluster is something like this, and the average of all the points in this cluster is something like this. So this would be centroid 1, and this would be centroid 2. Okay. So now the thing here is we want to remember that what the k-means clustering algorithm is trying to do is it's trying to find the overall best clustering that minimizes the inertia of that given clustering out of all potential clusterings that you could consider. Let's just say with two clusters here. So the question is, can we think of a different place to put these centroids such that our resulting clustering inertia would be even smaller than the inertia that this given clustering produces? So let's do a poll. So can we think of a better location for the centroids to be such that the resulting inertia would be even smaller than the inertia of this clustering? And by the way, not sure is always a valid answer if that's what you think. I like to see that. Okay. All right, so slight majority for no. So yeah, generally speaking, this in fact is going to be the best possible location of these two centroids, such that the overall inertia is in fact minimized. And so we want to think about, where else might we put these two centroids? Particularly, where might we put them such that we don't end up getting like the same clustering altogether? I mean, so the thing here is like it's possible that maybe we could have put like a centroid here and a centroid here, but nonetheless, each of these observations are still closest to this centroid. Each of these observations are still closest to this centroid. So we would end up with the same two clusters nonetheless. So the thing here is, basically, if we were to put those centroids any other location, like maybe if we were to put them here or here, the resulting amount of inertia of the observations assigned to that centroid would be markedly larger than the inertia that we would end up getting if we simply just had these centroids in these locations. And so again, our inertia is the sum of the squared Euclidean distances of all observations to their respective centroids. So this looks, generally speaking, relatively small. So tentatively, because of this, because the particular means of these clusters that we're actually trying to identify here are in fact the best location for those centroids to minimize the inertia. Because of this, k-means, even though we don't meet all the ideal properties, we can guess, successfully be able to identify the clusters that we see here. So the answer is yes, because these are the means of these two clusters do in fact produce the lowest overall inertia. Okay. Now, furthermore, we want to think about, well, okay, so k-means even though these clusters are not spherical, k-means still would be able to identify these two clusters if we were looking for two clusters. But the next question is, well, can we trust the k-means elbow plot to identify that there's two inherent clusters that exist in the data set in the first place? So I'm curious what we think about that. So do we think that the k-means elbow plot method will be able to indicate to us that there are, in fact, two inherent clusters in this data set? So yes or no? So do we expect to see something like this? Okay. All right, so we're seeing a overwhelming majority say yes. So yeah, so basically when we look at the application in just a second, we will in fact see that even though these two clusters do not meet all the ideal specifications, because they are so well separated from each other, that the dip in inertia that you see going from 1 to 2 is going to be dramatically larger than any dip in inertia that you see going from, say, 3 to 4 or 4 to 5. So to think about this, you can try to basically think about how might k-means cluster this given data set into one cluster, two clusters, three clusters, four clusters. And then again, you want to remember when k-means is trying to cluster a data set, it's trying to find the clustering Sorry about that. Okay. Can you guys hear me? We're good. Okay. Yeah, hopefully that should not happen too often. What's really surprising is why it chose to kick me off in my smaller class as opposed to my class with 200 people in it. But anyways, okay. So let's actually cluster this data set here. And let me make sure I'm recording. I am recording. Okay. So let's move on to the application. Give me just 1 second to set up the chat again. Okay. So, all right, so we're going to use k-means clustering again. And we're going to go through a series of two-dimensional scatter plots just for learning purposes and basically see what the k-means clustering algorithm will do when we cluster the data set. So this is what this data set looks like using the scatter plot function. And again, we're just going to cluster the x and the y attributes here. Okay. Now let's just say, for instance, we knew ahead of time that we were looking for two clusters. So we're going to use the k-means function and cluster it into two. So fitting just this x data frame here. Okay. And so let's think, so let's see, these are the k-means cluster labels that were returned. And again, we're going to add our cluster labels as a column in our df data frame. So this is our k-means cluster labels here. And so we'd like to see how well our actual k-means clustering did. What we can do is we can plot our data set using the Seaborn scatter plot function. Sorry about that. All right. If it does this two more times, we'll have to come up with a workaround. Okay. So we can see that k-means did in fact identify what we're looking for. And another thing that we can extract from k-means, if we're interested, is also the location of the final centroids for each of those two clusters. So we can use the cluster centers attribute that corresponds to that given k-means clustering object. Okay.
Professor.
Yep.
You share the screen.
Oh, sorry about that. Yeah. Okay. There we go. Okay. Yeah, so we can use the cluster centers attribute here. And so for instance, if I wanted to seconds, mute our mics. So if we wanted to visualize the centroids that we just found, we can, for instance, put those centroids into another pandas data frame. I'm just basically putting those cluster centroids into a pandas data frame, and I'm giving that data frame the same column names as the data frame with all of my observations in the data set. And so by using the scatter plot function twice, first for the original data set, and secondly for the data set that contains the centroids, I can in fact overlay the centroids for each of those two clusters that I found here. Okay. And furthermore, if I want to use the k-means elbow plot, so we've already kind of given the code for this elbow plot here, so we won't go through it again. But yeah, so basically we can in fact see okay, it very much seems like my Wi-Fi is not cooperating with me.
Bye.